Hey everyone, welcome to this new story. Before we go anywhere, take a moment to get comfortable. Let your body settle into the place you've chosen for the night. Shift your pillow if it helps. Let your shoulders relax and allow the weight of the day to ease away. There's nothing you need to focus on right now, nothing you need to remember. For the next 2 hours, you won't be asked to think, respond, or make any decisions at all. In this story, you'll be gently carried on a slow, uninterrupted flight above the surface of an alien ocean planet, its waters endless, shimmering under a distant sun. There will be no sudden turns, no surprises, just a smooth, steady journey, designed to help your breathing slow and your thoughts soften as you listen with your eyes closed. I'll be here at the beginning to guide you in, and then, gradually, I'll fade into the background as you follow this world with your imagination, letting its waves and currents fill your mind. As we begin, picture yourself floating, supported, safe, and unhurried. Below, vast oceans stretch endlessly, reflecting faint light dotted with islands or floating ice, moving in patterns shaped by unseen forces, ancient and alive. We'll explore it together, gently, at a pace made for rest. For now, just lie still and allow the journey to begin. We are approaching the planet slowly, observing it from a distance that allows the whole sphere to be seen against the blackness of space. The planet is large, much larger than Earth, with a round form that seems soft in its edges. As we move closer, the upper layer of the atmosphere comes into view. It is not a single color, but a mixture of pale blues, greens, and hints of gray. Light from the nearby star grazes the edges of the clouds, giving a sense of depth and motion. The rotation of the planet is noticeable, slow but steady, turning the clouds in gentle arcs across the surface. You can see some patterns repeating as the atmosphere moves, though they do not form sharp shapes. They flow, blending into one another as if painted in slow strokes. From this height, the ocean below is only hinted at, the surface reflecting tiny glimmers of light where clouds part. But the vastness of liquid remains hidden beneath layers of atmosphere. The planet's size is immediately clear. Compared to the orbiting spacecraft, it seems to stretch beyond a single glance, a sphere that could hold many Earths within its volume. You can sense the pull of gravity, though we are still in orbit. It is stronger than Earth's, but from this distance the feeling is subtle, a reminder of the planet's mass and the invisible force it exerts. The clouds at the top move in streaks, and you can imagine the winds below, turning and swirling unseen. There is a quiet power in the motions, the kind that does not shout but simply exists, steady and continuous. We are observers here, watching and waiting, letting the eyes and mind adjust to the scale of the world. The light shifts slowly as we approach the day side of the planet. Shadows of clouds fall across the surface, stretching like soft curtains. The sun, smaller than we are used to on Earth, but still bright, casts long, angled light that makes the upper clouds appear layered. Some are thin and high, allowing light to pass through them, giving the sense of almost transparent veils. Others are thick and full, reflecting light in bright, flat surfaces that make them seem solid, almost tangible. The movement of the cloud tops shows the planet is alive in a way that feels calm but intentional. Nothing is sudden, nothing is rushed. Every rotation, every swirl is part of the planet's natural rhythm. As we descend slowly, the curvature of the planet becomes more obvious. There is a subtle horizon where the sky and the cloud tops meet, a soft line that bends gently. From here, the color gradient of the atmosphere is clear. Near the upper edges, where the sun meets the planet's side, the colors are pale and almost white, fading into greens and blues as we look downward. The thickness of the atmosphere is visible in the way light bends around it, creating a soft glow that frames the planet. We can almost sense the weight of the air, even knowing it is not like Earth's air. The mixture of gases is heavier, and the density changes with height, producing layers that shift the way light moves through them. This layering is subtle but noticeable, a gradual change from top to bottom. We adjust the perspective, moving closer to see details in the upper clouds. Some of them have streaks running in long, narrow bands formed by winds high above the surface. These bands stretch for hundreds of kilometers, curving with the planet's rotation. The patterns are not uniform, but there is a rhythm to them. Occasional breaks in the bands reveal glimpses of the lower clouds, which move more slowly, hinting at different wind speeds and pressures. The upper atmosphere is cooler, thinner, and moves faster. The lower layers are warmer, denser, and respond more slowly to planetary rotation. This difference in motion is what gives the clouds their layered appearance from space. Occasionally, small circular formations appear in the clouds, tiny storms that rotate around a central point. They are not violent in appearance, but they carry energy. These storm cells move with the wind patterns, blending into the bands or drifting between them. Some are bright at the edges, catching the light, while others are darker, hinting at thickness or perhaps moisture content. Each formation is unique, shaped by the dynamics of the atmosphere. Watching them provides insight into how the planet's weather functions. The movement is constant, almost imperceptible from afar, yet over time, the change is clear and measurable. The shadows created by these clouds play across the unseen ocean below. Even without seeing the water directly, the surface can be understood in part by observing these patterns. Lighter areas suggest thinner cloud cover, or calmer sections below, while darker shadows indicate thicker clouds or denser regions. The ocean's presence is sensed through the interaction of light and cloud motion. Reflections from the sun are scattered across openings, giving a subtle shimmer that hints at the liquid layer beneath. This shimmering is not fixed. It moves with the clouds, appearing and fading, a silent signal of the world below. Our descent continues, and the atmosphere grows denser as we approach the top of the cloud layer. The air is no longer transparent, but diffused with a soft scattering of light that gives a diffuse glow to the surroundings. The uppermost clouds are thin and high, allowing glimpses of the layers below. Some are almost invisible from a distance, but now their forms can be seen in detail: fibrous textures, delicate edges, and faint color variations. These clouds move faster than the lower ones, caught in strong upper winds, while lower clouds lag behind, heavier and slower. The contrast creates a natural layering, a visible history of motion and energy. Looking more closely, we notice that the cloud tops reflect the star differently in places where their thickness changes. Thin sections let light pass, creating softer patches of brightness, while thicker areas reflect strongly, creating flat, bright surfaces that look like mirrors. Some areas appear slightly iridescent, with subtle hints of green and blue, possibly caused by chemical reactions in the clouds or the scattering of light through particles suspended in the air. This subtle play of color and brightness gives the upper atmosphere texture and depth, helping the mind understand the complexity of what we are seeing without needing to look below. The overall rotation of the planet becomes more obvious as we follow the movement of the clouds. They travel in long arcs, curving with the planet's spin. The curvature of these bands is gentle near the equator and slightly tighter toward higher latitudes, a visible sign of the planet's rotation speed. These motions are slow but steady, giving a sense of rhythm. We begin to appreciate the forces that guide the atmosphere: gravity pulling down, heat from the star warming the layers differently, and rotation shaping the paths of winds. The interplay of these factors produces the patterns we see, and observing them quietly reveals the natural order of this alien world. As we move laterally along the orbit, the day side of the planet reveals more subtle textures. Some areas have smoother cloud formations, while others are rougher, with small ridges and rounded forms. These differences could be caused by temperature variations, chemical composition, or winds interacting with each other. There are no sharp lines or sudden changes. Instead, everything flows gradually, blending from one pattern into another. Observing this teaches the mind to notice subtlety, to track motion without rushing, and to understand the complexity of a system through simple visual cues. The light itself changes subtly as we follow the planet. Reflections on the cloud tops shift with angle, revealing gentle slopes and the three-dimensional structure of the atmosphere. Where the clouds are thin, shadows from higher clouds reach down, creating soft gradients. Where clouds are dense, the tops appear almost solid, blocking light entirely and forming defined but soft shapes. Even at this stage, the interaction between light and structure is evident, giving a sense of the volume of air and the energy within it. The mind can perceive movement, density, and layering without needing to imagine anything beyond what is visible. From this vantage point, the planet is not simply a ball of gas or liquid, but a complex, interconnected system. Each cloud, each streak, and each shadow contributes to the overall motion. The upper atmosphere dances in response to forces below, while the surface below the clouds remains mostly hidden, waiting to be revealed. There's a sense of balance here, a steady flow of energy, a natural order that is neither chaotic nor rigid. Observing the planet in this way brings awareness to scale, to motion, and to the simple beauty of structure and rhythm in nature. As the descent continues, we begin to see the edge of the topmost cloud layer in greater detail. Individual clumps of vapor stretch in soft lines, curving gently around areas of higher density. The colors remain muted, pale shades of green and blue intermingled with gray. The wind above carries them in arcs, creating patterns that are neither perfect nor random. Each line tells a story of movement, of energy transmitted across the upper atmosphere. Watching these clouds move slowly encourages the observer to let their own breathing and attention slow, to match the natural pace of the world unfolding beneath the gaze. The subtle changes in light, color, and movement create a sense of immersion. Even without touching the surface, we feel close to the planet. The gentle rotation, the layered clouds, and the reflection of light hint at the existence of a vast, liquid ocean below. The upper atmosphere does not conceal the planet, but guides observation, offering glimpses of structure and motion while maintaining a protective layer above the surface. From this perspective, the mind can begin to imagine what the ocean might look like, how it behaves under the influence of the winds and the planet's gravity. This initial approach, this first close observation of the alien ocean planet, establishes the foundation for understanding what lies below. Every detail in the clouds, every subtle shift in light and shadow, every gentle rotation reveals information about the planet's atmosphere and hints at the ocean beneath. The perspective is slow, allowing the observer to take in patterns, colors, and movement without haste. Each observation builds upon the last, forming a continuous awareness of the planet as a whole, preparing the mind to enter deeper into its atmosphere and eventually to reach the surface of the alien ocean itself. The upper layers of the atmosphere reveal themselves as we descend slowly through the clouds. From above, the pale green and blue of the top layers gradually deepen into more complex tones. The gases that form the atmosphere are not like Earth's air. Hydrogen dominates the outer reaches, light and thin, while methane adds a subtle green tint. Deeper down, traces of ammonia and other compounds create gentle variations in color, softening transitions between layers. There's no sharp boundary where one layer ends and the next begins. Instead, the atmosphere shifts gradually, each part blending into the one below, forming a continuum of color and density. The thickness grows as we move closer to the surface, and the feel of weight becomes more apparent, even though we are still in orbit. We move laterally to follow the motions of the clouds within these layers. The uppermost clouds are thin, almost transparent, curling in arcs that extend for hundreds of kilometers. Their motion is steady and continuous, driven by winds moving swiftly across the high reaches. These winds are not chaotic. They follow predictable paths dictated by the planet's rotation and temperature differences. In places, small ripples run across cloud tops, slight disturbances that carry the energy of distant storms below. Each ripple is subtle, barely noticeable at first, but as the observation continues, the patterns become clear. They tell the story of air in motion, of heat rising and sinking, of pressure changing across the layers. As we descend, the clouds become thicker and more textured. The paleness of the upper atmosphere gives way to deeper greens and muted blues with gray streaks threading through them. Some clouds appear almost layered like sheets, stacked one above another with soft gaps in between. Others form gentle swirls, the edges curling under the influence of winds that change direction with height. The layering is natural, a reflection of how the atmosphere is structured. The upper layers are lighter and move faster, while the lower layers are denser, slower, and warmer. Observing these differences provides a sense of how the atmosphere works, how energy moves from the star to the surface below, and how each layer responds in its own way. The motion of storms becomes visible in certain sections. Tiny circular systems form and drift slowly, spinning around small centers. They are not violent or threatening, they are part of the natural rhythm of the atmosphere. Their edges catch the light, forming soft halos that stand out against the smoother cloud fields. Some of these storms combine with the surrounding clouds, stretching the pattern into elongated shapes that travel along the paths of upper winds. These patterns are constantly shifting. Watching them without haste allows the mind to track their subtle changes, to notice how pressure and temperature guide their paths. Sound in this environment is mostly absent. There is no wind to feel on our skin, no rushing or hissing. Instead, there's the silence of space, punctuated only by the faint hum of the spacecraft instruments. This quiet allows for focus, a way to notice the smallest movements of the clouds. Without sound to distract, the visual patterns gain prominence. The mind can follow the rhythm of the atmosphere, sensing currents and flows as they happen. Even without hearing, one can almost imagine the gentle motion of air above the surface, the shifting of gas molecules in response to temperature gradients, the soft lift and fall of pressure waves traveling across the planet. Deeper in, the clouds take on a heavier appearance. They become almost solid in places, thick with condensation. The color shifts toward darker greens and pale grays, with occasional hints of blue where light filters through thinner patches. The density of the atmosphere here slows the movement of the lower clouds. Winds are present, but they do not whip or rush. They slide along slowly, pushing the cloud masses in long, steady flows. Observing these flows teaches the eye to follow subtle changes in shape, to note where the wind gains or loses strength, and to see how temperature and pressure interact with density to shape what is visible. The interplay of layers creates a natural mosaic. Some clouds float high and thin, catching sunlight in soft highlights, while others lie lower, casting shadows that stretch over wider regions. The shadow patterns reveal the depth of the atmosphere. They move gradually as the winds shift and the planet rotates. By following these movements, it becomes possible to sense the structure of the atmosphere without touching it. Each layer contributes to the overall texture, forming a living canvas that reflects the energies and forces at work. Occasional breaks in cloud cover reveal glimpses of the ocean below. Light passes through these openings, refracted slightly by the layers of gas. The ocean appears distant, hidden behind the thick veil, but hints of movement show through. Small sparkles catch the light, suggesting ripples on the water's surface. These glimpses provide a connection between the atmosphere and the planet below. It is clear that the clouds respond to conditions at the surface, shifting and twisting in subtle patterns that carry information upward. Watching these moments reinforces the sense of continuity between sky and ocean. Temperature changes with altitude are gradual but significant. The upper layers are cold, almost at the edge of freezing, while the middle layers hold moderate warmth. Deeper clouds indicate warmer air, responding to energy coming from the surface or trapped within the lower atmosphere. The result is a slow movement of heat, upward and downward, driving circulation and creating the banded structures we see from orbit. Each layer moves at its own pace, influenced by temperature differences, rotation, and pressure. Observing these differences in motion reveals the natural order, a balance between forces rather than a chaotic system. Cloud formations themselves show complexity in shape and pattern. Some curl into elongated rolls, long bands, stretching across thousands of kilometers. Others form cellular structures, clusters of rounded cloud masses pressed together, each with slight variations in height and thickness. These shapes reflect local interactions between gases and temperature and wind speed. The variety is subtle but noticeable, a study in the many ways energy manifests in the atmosphere. Observing slowly, the viewer can see how each layer interacts with the others, how disturbances ripple through the system without losing overall coherence. Sunlight filtering through the clouds creates gradients of color. High layers glow softly with pale green and white, while lower layers take on muted blues and hints of gray. Where sunlight hits thicker clouds, brightness intensifies in localized patches. Shadows stretch across adjoining clouds, softening edges and creating a sense of volume. This gentle play of light highlights the three-dimensional structure of the atmosphere, giving depth and form to what might otherwise appear flat. By moving the perspective slowly, the mind notices transitions, the flow from layer to layer, and the quiet rhythm that guides them. Occasional streaks of wind can be traced by watching clouds thin along narrow paths. These streaks are not sudden gusts, but persistent flows that move consistently in one direction. They twist slightly as they interact with neighboring currents, forming gentle spirals and arcs. The movement is subtle, yet it carries energy over vast distances. Following these streaks allows the observer to appreciate the continuous motion, the way the atmosphere conveys energy and momentum, the way one part affects another without abruptness or chaos. The appearance of small, transient clouds adds another layer of interest. These clouds form where local conditions allow condensation, then fade away as the wind and temperature change. They drift above or between thicker layers, casting tiny shadows on the clouds below. Their formation and disappearance are not abrupt, but gradual, like the slow breathing of the planet. Observing this slow cycle encourages the mind to settle into the rhythm, to watch without expectation, noticing movement as it unfolds naturally. Looking horizontally across the planet, the curvature is still visible. Bands of cloud stretch toward the horizon, curving gently as they follow the spin of the planet. Upper winds tug at the edges, lower clouds lag behind, and together they form a flowing system of motion. The speed and direction of each layer are measurable yet smooth. There is no harsh turbulence, only gradual shifts and rotations. Watching this carefully demonstrates how forces combine to create order, how planetary spin, temperature, and gas composition govern atmospheric behavior. Small vortices sometimes appear where layers interact. These are miniature storms, spinning slowly, often in areas where warmer lower clouds meet cooler upper clouds. They remain contained and small, providing visual interest without disturbance. Each vortex communicates information about the local atmosphere, pressure differences, temperature gradients, and the response of the gases to motion. Observing these forms develops an understanding of the complexity of the system, how energy flows without chaos, and how slow movement allows for long-term patterns to form naturally. Even deeper in, the clouds are denser still. They merge, forming continuous layers that block most light from passing. The upper light filters in faintly, creating soft glows in places. Wind is present, though barely perceptible, moving the clouds in extended languid flows. The texture of the clouds becomes more pronounced. Swells and bulges appear, showing the effect of convection as warmer gases rise and cooler ones sink. Observing these swells highlights the vertical movement in the atmosphere, a hidden motion revealed only by the shifting forms above. The overall atmosphere is a combination of continuous motion, layered density, and color variation. Each layer responds to the star's light, the planet's rotation, and interactions between gases. There is no sudden change, no abrupt disturbance, only a steady flow from one part to the next. This slow movement is mesmerizing. Watching the planet in this way encourages patience, focus, and a gentle awareness of natural forces. The mind becomes attuned to subtlety, noticing differences in speed, direction, and structure that would otherwise go unnoticed. As we continue, the horizon stretches, showing long bands of cloud moving in arcs. Upper layers glide faster, tracing paths shaped by the planet's rotation. Lower layers follow with a gentle delay, creating a stacked effect that reveals depth. The interplay of light, shadow, and movement gives a sense of three-dimensionality. Even without seeing the surface below, the atmosphere communicates its structure clearly. Each observation reinforces the idea that the planet is a cohesive system where motion, energy, and material interact continuously in predictable ways. Occasionally, faint wisps of lighter clouds rise from below, threading upward through the thicker layers. These formations suggest updrafts, areas where warmer air moves upward, carrying moisture or gas with it. The rise is slow, the path curved and smooth, blending with surrounding layers. Watching these wisps provides insight into how energy is transported vertically and how local conditions create small, temporary structures that complement the larger motions of the atmosphere. Every layer is in conversation with the others, forming a quiet, balanced system that moves without haste or abruptness. As we descend through the final layers of the atmosphere, the ocean begins to reveal itself more clearly. Its surface stretches far and wide, a continuous expanse that seems to move gently beneath the clouds. From this height, the color is soft but varied, shifting from deep green in some areas to pale blue in others. Differences in color hint at variations in depth, temperature, or perhaps chemical composition. The light from the star above reflects differently, depending on the angle and the smoothness of the surface. Some areas catch the sunlight sharply, forming thin streaks of brightness that follow the curvature of the waves. Other sections appear muted, reflecting only a faint glow from scattered light above. The texture of the ocean is subtle but noticeable. Small undulations ripple across the surface, moving in patterns that suggest slow winds above and currents below. There are no sudden waves crashing. Instead, the motion is continuous and predictable. Each ripple interacts with its neighbors, forming small networks of peaks and troughs that shift over time. The surface does not appear flat or uniform. Instead, it holds a quiet complexity, as if it is breathing gently in response to the energy moving through the atmosphere and the liquid itself. Looking more closely, some waves appear, slightly larger, elongated along paths that suggest prevailing winds. These waves are smooth, lacking foam or white caps, which could indicate lower energy or differences in the fluid's composition. In some regions, the ocean has a slightly glassy appearance, reflecting the clouds above with faint distortions. Light bends and scatters as it passes through thin ripples, creating a gentle shimmer that moves slowly across the surface. Observing this shimmer helps to understand the way the liquid interacts with light, revealing subtle curves and angles in the waves that might otherwise go unnoticed. Currents begin to emerge as we follow the surface across broader areas. Certain sections move more quickly, forming narrow bands where the motion is consistent. Other regions appear almost still, held in place by opposing flows or differences in density. The interplay of currents is continuous, forming patterns that are always changing, yet follow underlying rules. These flows affect the surface in ways that are visible from above. Slight ridges form where currents meet, small depressions appear where water converges, and gentle swirls appear at intersections. Watching these subtle movements provides insight into the energy flow within the ocean and the forces that shape it. The surface shows faint differences in texture. Areas of calm water are smooth and mirror-like, reflecting the clouds above in soft, distorted images. Sections affected by currents or wind have small ripples and patterns that scatter light differently. This variation is continuous, never abrupt, and creates a natural rhythm across the planet's liquid surface. In some places, thin streaks appear, where the water is disturbed gently by winds or localized motions beneath. These streaks move slowly, forming subtle lines that trace the paths of energy across the surface. The interaction of light with the ocean is complex. Sunlight reflects directly in certain areas, forming bright points that shift as the waves move. Indirect light passes through the liquid near the surface, scattering slightly and giving a faint glow in shallow regions. Where the water is deeper or denser, reflections are muted and color appears darker. Light bending at the edges of waves creates small variations in tone, highlighting the curves and slopes of the liquid. Observing these shifts carefully reveals the shape and motion of the ocean, even without touching it. Some sections hint at subtle textures beneath the surface. Gentle currents stir the liquid, creating faint waves that move slowly and steadily. The patterns are not chaotic, but layered and continuous, forming a dynamic system that can be read by careful observation. Changes in color, reflection, and motion all provide clues about what is happening below the visible layer. These differences might indicate variations in depth, temperature, or even the chemical mix of the liquid. Each observation builds on the last, forming a cohesive picture of the ocean as a living system responding to its environment. Small, occasional patches differ from their surroundings. In some regions, the water appears as slightly lighter or darker, suggesting local changes in density or composition. In others, the liquid seems smoother, reflecting clouds more clearly. These variations are subtle, but they give character to the surface, showing that it is not uniform. Energy moves through these areas differently, forming small currents and ripples that spread outward. Observing the differences teaches how the liquid responds to forces, creating patterns that are both predictable and varied. The curvature of the planet is visible even at this level, and the surface seems to stretch endlessly toward the horizon. Bands of reflection and shadow follow the gentle curves of waves, moving slowly as the planet rotates. The overall effect is calming, a sense of continuity and balance. The ocean does not rush. It flows steadily, shaped by internal currents and the atmosphere above. Observing from this angle allows the mind to understand the scale of the surface, the slow motion of water, and the quiet interactions between light, wind, and liquid. Temperature differences across the surface affect motion subtly. Slight variations in warmth create gentle shifts in the liquid, influencing currents and ripples. Areas warmed by the star's light may appear more luminous or reflective, while cooler sections remain muted. The contrast is never sharp, only gradual, blending from one area to another. Watching these transitions encourages attention to subtlety, to the way energy moves slowly across a large body of liquid. The ocean seems alive in its motion, yet calm, predictable, and continuous. Light and shadow interact with the waves in ways that reveal three-dimensional structure. Sunlight forms thin streaks along ridges, highlighting small peaks. Shadows follow the troughs, soft and elongated, Where waves are flatter, reflections from clouds above create gentle, distorted images. The combined effect gives depth and texture, allowing observation to read the shape of the ocean without touching it. Movements are subtle but continuous, emphasizing the slow rhythm of the system. Some sections of the ocean hint at small floating debris or particles. These could be natural formations, perhaps dense patches of chemicals or small mineral fragments. They move with the currents, slowly following the flow of energy across the surface. Their presence slightly changes reflections and adds detail to the scene, emphasizing that the ocean is not static but a responsive system. Watching them drift reinforces the sense of continuous motion, connecting the eye to the underlying forces at work. Occasional small swirls form where currents intersect. These eddies are subtle, circular movements that do not disrupt the overall flow. Their centers are calm, while the edges rotate slowly, blending with surrounding currents. Each swirl tells a story of interaction, showing how movement in one part of the ocean affects adjacent areas. Observing them patiently allows the mind to see how energy propagates, forming patterns that are subtle but persistent. The surface also reacts to variations in wind above. Gentle flows create small ridges and shallow troughs, forming networks of parallel lines that move slowly across the water. Some of these lines extend for long distances, curving slightly as the planet rotates. They are not violent or sudden, but persistent, visible evidence of the connection between atmosphere and ocean. Watching these interactions encourages focus on subtle cause and effect, noticing how small changes propagate across large areas. Some areas show hints of refracted light. Sunlight passing through thin waves bends slightly, forming soft, shifting patterns on the surface below. This bending gives the water a three-dimensional appearance and reveals slopes or curves that are otherwise invisible. The refractive effects are subtle, moving with each small ripple, and contribute to the overall sense of texture and motion. Observing them slowly allows one to understand the depth and behavior of the ocean. The ocean's surface appears continuous, but careful observation reveals small variations that give it character. Slight differences in reflectivity, wave height, or movement form an intricate system. Nothing is abrupt. All changes happen gradually, and each contributes to the overall rhythm of the liquid. The mind can follow these patterns without rushing, noticing details and interactions that form a comprehensive picture of motion, texture, and energy flow. Currents and waves interact smoothly, forming layered movement across the surface. Bands of faster flow slide past slower areas, creating gentle gradients in speed and direction. Waves adjust subtly as they encounter these currents, forming elongated shapes or gentle swells. The combined motions are continuous, creating a visual story of energy moving steadily across the ocean. Watching this carefully encourages the observer to notice small, repeating patterns, how one motion influences the next, and how the surface is a reflection of forces both above and below. As we continue across the planet, the ocean seems endless. The texture, motion, and reflectivity create a complex, continuous pattern that is calming to observe. Each wave, each current, each shimmer of light contributes to a slow-moving, cohesive system. By watching closely, the observer gains a sense of how the planet functions as a whole, how the atmosphere and ocean interact, and how energy flows through the liquid surface. The experience is steady, immersive, and completely grounded in observation. Looking down at the alien ocean from just above its surface, it becomes clear that the liquid is not the same as the water we know on Earth. Its composition is different, influenced by the planet's temperature and chemistry. There are signs that the liquid could be a mixture of water and ammonia, creating a solution that behaves differently than pure water. This mixture affects the way waves form, the way light moves through the liquid, and even how currents interact across the surface. The chemical makeup influences everything we see, from color variations to the subtle ripples caused by gentle winds. The color of the ocean is not uniform. Some regions appear greenish, others have a bluish tint, and still others show pale gray patches. These differences are partly due to chemical composition. Areas with higher ammonia content can appear lighter or more reflective, while sections with more water or other hydrocarbons might appear darker. Sunlight passing through these regions scatters differently depending on the density and makeup of the liquid. Observing these shifts slowly, we can begin to understand how the chemistry affects the visual appearance of the ocean. Temperature plays an important role in the behavior of the liquid. Surface temperatures vary slightly with location, affected by sunlight, cloud cover, and local currents. Warmer regions are more fluid, with subtle ripples that move faster and spread more easily. Cooler areas appear thicker, slower to react to disturbances. Even small changes in temperature affect wave patterns and the interaction between currents. Understanding these variations provides insight into the overall energy balance of the ocean and how it interacts with the atmosphere above. Density changes gradually with depth. The liquid near the surface is lighter, responding more easily to wind and surface motion. As we look deeper, the liquid becomes denser, influenced by chemical composition and lower temperatures. These variations form layers within the ocean, each with slightly different behavior. Currents can shift between layers, creating vertical motion that affects surface patterns and overall flow. The layering is continuous and subtle, but it is present everywhere, shaping the appearance and dynamics of the ocean. Salinity, or its equivalent in this alien chemistry, also influences movement. Dissolved compounds alter the weight of the liquid, affecting how it responds to gravity and winds. Areas with higher solute concentration may have slower, more stable currents, while regions with lower concentration can move more freely. The interactions between temperature, density, and chemical composition produce a complex but steady system of motion that can be observed carefully from above. Watching these effects helps the mind recognize patterns and relationships in the fluid. The surface behavior is a direct reflection of the ocean's chemistry. Waves and ripples form differently depending on the mixture of substances in the liquid. Some regions appear smooth and glass-like, while others show faint turbulence. These variations are not random. They respond to the physical and chemical characteristics of the ocean, as well as the energy delivered from winds and light. Observing these subtle differences allows the viewer to understand how the ocean is structured and how it reacts to external forces. Light interacts with the liquid in multiple ways. In shallow regions or areas with less dense chemical content, sunlight penetrates slightly, creating faint reflections and a soft glow. In deeper or denser regions, light is absorbed or scattered differently, giving the surface a darker, more muted appearance. Reflections from clouds above are also affected by the composition of the ocean. Some surfaces appear sharper, almost like mirrors, while others distort light gently. This variation provides clues about the properties of the liquid, its density, and its chemical makeup. Small surface variations reveal localized chemical differences. Some patches appear slightly more reflective or lighter in color, while adjacent areas are darker or more opaque. These differences suggest the presence of subtle currents or gradients in composition. As these small areas move and change with the flow of the ocean, they create faint, shifting patterns on the surface. Observing these patterns over time allows one to see the interaction between chemical properties, light, and motion. The ocean is not uniform, but it behaves in predictable ways based on its composition. Temperature gradients influence color and reflectivity. Warmer patches of liquid may appear brighter or smoother, while cooler areas are darker and more textured. These gradients are gradual and never abrupt, and they create soft transitions across the surface. Currents and waves interact with these variations, moving faster or slower depending on local conditions. This slow, continuous motion demonstrates how temperature and chemistry combine to shape the behavior of the ocean. Observing the interplay of color, light, and motion reveals the subtle mechanics of the system. Vertical mixing occurs where density and temperature differences are significant. Lighter surface layers may shift and tilt under wind or current pressure, while denser layers below resist movement. The interaction between these layers creates small, slow moving waves and subtle turbulence. These motions are barely noticeable at first, but careful observation reveals their presence. They form a delicate balance, contributing to the overall stability of the ocean while maintaining gentle motion across the surface. The result is a complex but continuous system that responds predictably to external forces. The chemical composition also influences surface tension. Areas with higher ammonia content may allow waves to form more easily or reflect light differently. In contrast, regions with higher density or different solutes may resist disturbance, creating smoother, more stable surfaces. These variations occur naturally and gradually, producing diversity in surface texture without abrupt changes. Observing this carefully allows an understanding of how chemical properties affect the visible behavior of the liquid. Light penetration is affected by the chemical mixture. Some components allow faint beams to pass, creating soft glimmers below the surface. Others absorb or scatter light, giving the ocean a deeper, richer color. Reflections from clouds in the sky above combine with these effects, producing a dynamic surface that responds to both internal and external influences. The ocean is alive in its chemistry, constantly interacting with light, energy, and motion. Each observation builds on the last, revealing more about the hidden properties beneath the visible layer. The smoothness or roughness of the surface is closely tied to composition. Areas that are chemically uniform appear calm and steady, reflecting clouds and sunlight in consistent patterns. Areas with varying solute concentrations show gentle irregularities, small ripples, or faint turbulence. Currents carry these differences across the ocean, spreading subtle variations in texture and motion. Observing these patterns teaches the eye to read the behavior of the liquid, understanding the effect of chemical and physical properties on its appearance. The ocean's chemical balance also affects density-driven motion. Slight differences in concentration produce small flows as heavier regions sink and lighter regions rise. These movements are slow and continuous, visible as faint undulations on the surface. Watching the surface over time reveals how these forces interact with winds and waves, shaping the continuous motion we see from above. The ocean is a system of energy and matter, responding predictably to chemical and physical influences while maintaining a calm rhythm. Temperature, density, and composition combine to form a layered living system. The surface reflects this in subtle ways. Slight variations in color, small differences in wave formation, faint changes in reflectivity. Currents carry these variations across vast distances, forming a dynamic but steady pattern. Observing this system allows the mind to understand how the ocean functions as a whole, how its chemical and physical properties interact, and how motion and energy are distributed naturally across its surface. Even in regions where the surface appears calm, the chemical properties continue to influence behavior. Light moves differently through varying densities. Ripples form or fade depending on local composition. Subtle shifts in temperature create gentle flows that affect adjacent areas. Watching these effects slowly without rushing allows one to perceive the ocean as an integrated system where chemistry, motion, and light work together to create a continuous, observable pattern. Small, faint swirls on the surface often mark transitions in chemical composition or temperature. These swirling patterns are slow, merging with currents and nearby waves. They are natural markers of variation, showing where one mixture meets another. Observing them carefully provides insight into the vertical and horizontal interactions within the ocean. Each swirl, each shift, each color change communicates information about the composition and movement of the liquid, forming a continuous story for the attentive observer. The ocean is not a uniform mirror, but a dynamic system shaped by its chemical and physical properties. Light and color and motion interact subtly with temperature, density, and composition. Variations are gradual, observable, and continuous, forming a surface that is complex yet calm. Watching this carefully builds an understanding of how the alien ocean behaves, how it responds to environmental forces, and how its composition defines the patterns we see from above. Gradually, the understanding of the ocean deepens. Each observation of color, motion, and light is a lesson in chemistry and physics. Each ripple, wave, and reflection connects to the underlying properties of the liquid. The ocean surface is a continuous, calm, and responsive system shaped by the combination of temperature gradients, density layers, and chemical mixtures. Observing it slowly allows the mind to grasp the intricate balance of forces that govern its motion and appearance, providing a foundation for exploring the deeper layers and currents beneath. As we glide closer to the surface, small floating features begin to appear. Some are irregularly shaped formations that rise slightly above the liquid. These could be mineral clusters that have crystallized and broken free, floating gently on the surface. Their edges catch the light, forming soft reflections that move as waves shift beneath them. Others appear as larger floating bodies, shaped by differences in density between the solid and the liquid. They drift slowly, following the currents, rotating occasionally when pushed by subtle waves. Each one interacts with the surface around it, forming small wakes and ripples that radiate outward in gentle arcs. Some of these formations are translucent, allowing light to pass through partially. Sunlight refracts slightly as it moves through the edges, creating faint glows in the surrounding water. This effect emphasizes the three-dimensional nature of the features. Looking closely, you can see subtle patterns on their surfaces, stripes, pits, and grooves that hint at how they formed. Some have flat tops, while others are domed or irregularly angled. Their diversity in shape and texture contributes to the natural complexity of the ocean's surface, providing points of reference in an otherwise continuous expanse of liquid. Beneath the surface, larger submerged features influence currents subtly. These could be ridges or denser mineral deposits that change how water flows above them. As currents move over these submerged forms, small eddies form at the edges. The surface reacts slowly, forming faint ripples or gentle twisting motions in the water. Observing these interactions carefully, it becomes clear how even features below the surface shape the visible patterns above. No movement is abrupt. The water responds gradually, reflecting the balance between density, gravity, and chemical composition. Islands, if present, appear small from this height, but show distinct effects on the surrounding liquid. Currents flow around them, forming slightly faster streams along their edges and slower zones in their wake. Shadows cast by the formations stretch across the water, softening the visual transition between the feature and in the surrounding ocean. Light moves differently along these areas. Brighter reflections may occur where the liquid is shallower or less dense near the edges, while deeper water in the wake appears darker. These variations provide subtle cues about scale and perspective, giving a sense of size without abrupt reference points. Floating crystals or ice-like bodies are rare but noticeable. They tend to align with local currents, drifting in groups or chains. Their presence slightly disrupts the flow, creating tiny waves or curved streaks that spread outward. Each ripple interacts with neighboring ripples, forming patterns that shift slowly across the surface. Over time, these interactions reveal how even small, isolated features influence the larger system. Watching these movements develops a sense of connection between objects, currents, and surface patterns. Surface patterns form naturally around floating features. Converging currents create gentle swirls, while divergent flows leave subtle depressions. These patterns move continuously, changing as currents shift or as features rotate and drift. Observing them from a fixed perspective, one can see how motion spreads across the surface. A small eddy near one object influences the ripples around it, merging with neighboring motions to create a dynamic but steady pattern. No sudden changes occur. The surface responds gradually to every disturbance, emphasizing continuity and balance. Wake patterns are evident behind larger floating features. The water immediately behind these objects moves more slowly, forming a slightly elongated depression. Ripples from the leading edges radiate outward, eventually merging with other waves. The effect is subtle, but noticeable when observed patiently. These wakes provide insight into the speed and direction of currents and how floating or submerged features shape them. Watching these slowly reinforces a sense of rhythm and connection across the surface, linking small details to larger movements. Scale and perspective are important when observing these features. From above, even large formations may appear small, while subtle ripples can seem pronounced. Distance, light, and the curvature of the planet all influence perception. Moving the viewpoint gradually helps interpret size and depth. The relative motion of waves, wakes, and floating objects allows one to measure scale without direct reference points. The ocean feels expansive, yet each feature has a distinct place within the continuous system of motion. Some submerged structures are visible through shallow water. Variations in color or reflection hint at ridges or denser regions below the surface. Currents passing over these features form faint swirls, often overlapping with surface ripples. Observing these areas over time shows how the hidden landscape beneath the liquid shapes the visible patterns above. Light bending through shallower regions adds subtle highlights and shadowing, further defining the form and orientation of submerged objects. The interaction between currents and features is continuous. A floating cluster slows slightly as it meets a small eddy, then is nudged sideways by neighboring flows. These motions create gentle rotations or shifts that ripple across the surface. Larger objects have more pronounced effects, forming extended wakes that influence surrounding areas for kilometers. Watching these interactions emphasizes the interconnected nature of the system, where every feature contributes to the overall rhythm of the ocean. Small floating fragments sometimes cluster together naturally. Their arrangement follows local currents, with slight spacing that forms repeating patterns. These clusters may drift slowly across the surface, rotating in response to the flow of the liquid. Observing them carefully, one can trace how energy propagates through the ocean, influencing the movement of solids and liquids alike. Each observation reinforces the continuous balance of forces at work. Some mineral formations float partially submerged, revealing only tops above the liquid, so the portion beneath affects local currents subtly, creating depressions and slight accelerations around the edges. Surface ripples trace these movements, allowing careful observation to detect the underlying structure. Even small features influence the motion around them, forming a delicate interplay between floating objects, submerged structures, and the liquid itself. The spacing of floating features affects surface patterns. When features are close together, ripples interact more frequently, forming complex yet predictable networks of motion. When spaced farther apart, currents flow more freely between them, and the patterns are smoother and more elongated. Observing these differences highlights how local arrangements influence overall dynamics. The ocean surface appears calm at first glance, but careful attention reveals a continuous system of interaction and balance. Reflections change around floating objects. Sunlight bounces differently depending on angles, surface texture, and curvature. Edges of features may appear brighter, while shadows stretch across the water behind them. These visual cues aid in understanding the position and shape of objects relative to one another. Slowly following these effects helps build a three-dimensional sense of the surface and its floating and submerged components. Eddies form naturally around submerged or floating features. Small circular motions appear at the edges of objects, spinning gently and merging with nearby currents. These eddies are subtle but consistent, tracing the energy flow from one area to another. Observing them over time reveals how localized features shape the surrounding liquid, emphasizing continuity and the slow propagation of motion across the ocean. Some floating features rotate slowly in place as currents push against them from different angles. This rotation affects nearby ripples, creating curved patterns that shift gradually. Watching these rotations develops a deeper understanding of the dynamic relationship between solid features and the surrounding fluid. Even minor movements contribute to the overall texture and motion of the ocean, forming a continuous story of interaction. The horizon shows the expanse of the ocean, dotted with floating and submerged features. Their relative size, spacing, and motion convey a sense of depth and scale. Even small clusters are meaningful, showing how localized effects ripple outward. Observing across a broad view allows perception of both individual details and the larger pattern. The ocean is vast, yet each feature has its role, contributing to the rhythm, motion, and structure of the surface. Submerged ridges are not always directly visible, but their effects on surface patterns are apparent. Gentle rises below the liquid create faint accelerations in currents above. Surface ripples follow these flows, tracing hidden forms beneath the water. Watching these interactions slowly allows the mind to read the hidden landscape through motion alone. The ocean becomes a continuous system, with each feature floating or submerged, shaping the visible and unseen patterns simultaneously. Small, ice-like formations, if present, reflect light brightly in the sun. They stand out against the darker liquid, moving with currents or floating independently. Their wakes and ripples interact with surrounding waves, forming complex but continuous patterns. Observing these slowly allows understanding of both motion and structure, showing how features both enhance and respond to the behavior of the ocean as a whole. The overall effect is a continuous tapestry of movement. Floating objects, submerged features, currents, waves, and light all interact naturally. Motion spreads gradually, reflecting underlying forces and chemistry. Observing with patience reveals an organized system where each component contributes to the larger rhythm. The ocean is calm, complex, and interconnected, a living network of motion and structure that rewards careful, unhurried observation. As we move slowly below the surface, the liquid changes in appearance. Light from above fades gradually, scattering in different directions. Some rays penetrate deeply, giving a soft glow, while others are absorbed quickly, leaving areas of gentle shadow. The water seems heavier here, denser than at the top, moving more slowly with each current. The clarity changes as well, depending on the concentration of chemicals and particles. Some sections remain relatively clear, allowing us to see several meters downward, while others are faintly clouded, scattering light in subtle patterns. Temperature decreases steadily as we descend. The surface is warmed slightly by the star, but deeper layers are cooler, forming layers that respond differently to currents. Denser liquids sink slowly, mixing with lighter layers above. This layering is continuous, forming a system that guides motion without abrupt shifts. The gradual cooling is reflected in the way ripples at the surface correspond to slower, steadier flows below. Observing these gradients gives insight into the ocean's energy distribution and how forces interact at different depths. Pressure increases as well, compressing the liquid slightly and influencing motion. Objects that float near the top respond easily to small currents, but as we move downward, movement becomes more resistant. Each layer carries the weight of those above it, creating a slow but constant tension that shapes the behavior of the ocean. Currents bend around denser layers, producing gentle undulations that ripple upward, affecting the surface in subtle ways. The interaction between pressure and density is continuous. a quiet but measurable force shaping the underwater environment. Below the surface, we begin to notice faint geological features. Ridges rise slowly from the floor, their tops rounded and softened by the surrounding liquid. Cliffs descend gently, forming shadowed areas where light penetration is minimal. Vent systems may release warmer, less dense liquid, forming thin streams that rise toward the surface. These plumes move slowly, merging with local currents, creating subtle eddies and swirls. Their presence affects both motion and temperature in nearby layers, adding complexity to the underwater environment without abrupt disruption. Light interacts with these features in distinct ways. Where ridges rise, rays bend around edges, forming soft shadows that emphasize contours. Reflections from suspended particles create delicate highlights, tracing lines along slopes and hollows. Observing these patterns carefully allows one to perceive shape and depth, even without clear visibility of the ocean floor. The combination of light, motion, and chemical composition produces a continuously shifting display, subtle but informative for understanding the underwater structure. Some areas show faint stratification of sediment or dissolved materials. Layers accumulate slowly over time, forming soft slopes or gentle rises. Currents interact with these layers, forming streaks and slight swirls on the surface of the sediments. These patterns are slow and predictable, a visual record of continuous motion. Observing them teaches how the ocean maintains balance between deposition, erosion, and flow. Even the smallest shifts reflect the interactions between density, temperature, and chemistry in the liquid. The vertical movement of water is gradual but significant. Heavier, cooler layers sink, while lighter, warmer streams rise. This circulation is continuous, forming a slow, layered motion that shapes the structure of the ocean. Rising currents carry dissolved substances upward, slightly changing color and clarity as they reach shallower layers. Descending flows carry denser material downward, creating faint streaks visible when light penetrates. These movements are not chaotic. They are part of a larger system that governs the ocean's behavior over time. Pressure, temperature, and chemical concentration all influence how currents bend around geological features. Ridges redirect flows, forming faint circular patterns downstream. Cliffs create gentle shadow zones where motion is slower. Vent systems create localized rises and eddies, affecting surrounding layers subtly. Observing these interactions over time gives a clear understanding of the continuous, layered dynamics of the ocean. Each element contributes to the overall motion, connecting surface patterns with deep currents. The ocean floor shows variation in texture. Some regions appear smooth and uniform, while others are rugged, forming low ridges or scattered formations. These textures influence the flow above them, guiding currents along gentle paths and producing subtle changes in surface motion. Light from above interacts differently with these areas, highlighting slopes and depressions with soft gradients. Watching the interplay of light and shape helps to perceive depth, structure, and scale in an environment that would otherwise seem uniform. As we descend further, visibility decreases, but motion remains apparent. Currents continue to flow steadily, forming patterns that trace the underwater landscape. Small eddies and circular flows develop around hidden features, their effects traveling upward to influence the surface. Subtly, the ocean remains continuous, connected from top to bottom, with each layer responding to temperature, pressure, and chemistry. Observation allows the mind to perceive these connections, to understand how energy and motion propagate through the liquid steadily and calmly. Submerged cliffs and ridges are not static. Their presence shapes the motion of adjacent water, producing faint, long-lasting flows along their slopes. The edges of these features form gentle shear zones where faster-moving currents slide past slower layers. These zones are gradual and continuous, contributing to the layered rhythm of the ocean. Watching the interactions slowly reveals how hidden topography governs movement, even far above the features themselves. Chemical gradients are noticeable at depth. Dissolved compounds concentrate differently in lower layers, affecting density and the scattering of light. These gradients subtly influence motion, forming areas where currents accelerate or decelerate. Light passing through these regions bends gently, creating faint patterns that trace movement. Observing carefully allows perception of depth and composition, providing clues about the structure and dynamics of the alien ocean without needing direct touch or measurement. Rising plumes from vent systems carry warmer liquid upward. As they ascend, they expand slightly and interact with surrounding currents. These plumes create subtle streaks and eddies on the surface of denser layers, visible as soft, moving patterns. They are slow, almost imperceptible at first, but they connect deep activity to surface dynamics. Observing these interactions demonstrates the continuity of the ocean's energy flow and the delicate balance between upward and downward motions. The underwater environment is continuous and integrated. Surface features, floating objects, and deep formations are all linked by motion, chemistry, and temperature. Currents flow steadily, guided by density and pressure differences. Light, while fading, continues to reveal patterns that inform about depth, slope, and material. Each observation contributes to understanding the alien ocean as a unified system where motion, composition, and light interact continuously to form a stable yet dynamic environment. Even in the dimmer depths, small variations in motion indicate the presence of hidden features. Faint undulations in currents signal ridges or depressions. Rising warmer streams reveal vent systems or less dense pockets. The interaction between layers remains subtle and continuous. Observing patiently, one can perceive the contours of the ocean floor and the overall rhythm of motion that connects surface to depth, revealing the ocean as a single, interconnected system. The deeper we look, the more apparent it becomes that the alien ocean is both calm and active, structured yet fluid, a continuous environment shaped by chemistry, temperature, pressure, and topography. Even without complex organisms, the alien ocean could host microscopic structures that move slowly through the liquid. These plankton like particles are shaped by the chemistry and physics of the ocean. Some float near the surface, carried gently by currents and waves. Others drift deeper, suspended in layers where density and temperature allow them to remain stable. Their movement is steady, continuous, following the slow rhythm of the liquid. Observing these structures carefully, one can see patterns in how they gather, disperse, or interact with small currents. The ocean is not empty. It is a system where matter circulates, shaped by natural forces and chemical gradients. Chemical gradients influence where these particles accumulate. Areas with higher concentrations of ammonia, hydrocarbons, or dissolved minerals can hold more particles, while other regions are relatively sparse. As currents move through these zones, they push clusters along, forming faint lines or swirls on the surface or within mid-depth layers. Even small disturbances, such as waves or localized eddies, affect the distribution subtly. Watching patiently reveals a continuous, dynamic pattern, showing how chemistry, motion, and buoyancy interact to shape microscopic ecosystems. Some particles reflect light differently depending on their composition. In areas where light penetrates the liquid, faint glows appear, highlighting their movement. These highlights are not bioluminescence in the way we understand it on Earth, but they create subtle visual signals that can be detected from above. As light bends through waves and ripples, these faint glimmers shift slowly, tracing the paths of currents and revealing patterns of motion invisible in darker or denser layers. Careful observation of these reflections allows us to see the hidden organization within the ocean. Temperature variations also influence particle behavior. Warmer zones near vents or shallow regions allows some structures to float more freely, while cooler layers may slow movement. Small currents carry clusters from one area to another, forming gentle streaks or faint patches. These motions are continuous and predictable when observed over time. Even without large organisms, the ocean has zones of activity shaped by physics and chemistry, creating subtle but observable patterns. At the interface between surface and water, tiny floating mats could form where particles gather. These mats follow local currents, expanding or contracting slowly as material is added or dispersed. Surface ripples move across them, bending and shaping their edges. When multiple mats drift near each other, they create overlapping patterns of motion, forming networks that trace the underlying flow of the ocean. Each cluster or mat responds continuously to wind, light, and liquid density, reinforcing the slow rhythm of the environment. Some regions might support structures that resemble faintly glowing lines if chemical reactions in the liquid produce energy differences. Small particles could fluoresce weakly, creating localized glows. These are very subtle and follow the natural layering of the ocean, appearing only where light and composition allow. Currents carry these glowing patches along predictable paths, merging with neighboring flows. Observing this over time reveals a quiet, organized display, showing how energy moves through the chemical and physical environment, even without larger life forms. The movement of these microscopic structures is always linked to currents and layering. Rising plumes of slightly warmer or lighter liquid carry particles upward, while denser flows carry others down. These vertical motions create faint, continuous mixing that slowly redistributes material. Over broad areas, the collective effect of millions of small particles traces the energy and flow of the ocean. Nothing is abrupt, all movement is gradual, following predictable rules of buoyancy, density, and fluid dynamics. Surface disturbances, even small waves, affect particles gently. A wave crest lifts some structures, then deposits them in a slightly different location as the water falls. Subtle ripples push clusters along narrow paths, while eddies at the edges of floating mats create circular movements. These interactions highlight the close link between physics and biology, showing how even tiny forms are integrated into the continuous motion of the liquid. Watching these changes develops an understanding of how structure and function can emerge naturally in such an ocean. Areas with slight chemical differences form microhabitats. Particles or mats tend to concentrate where dissolved compounds are richer, creating faint zones of activity. Adjacent regions may remain less populated. Currents carry clusters from one zone to another, maintaining a dynamic balance. These patterns are stable over time, but continuously shifting, showing how energy, chemistry, and motion shape potential ecosystems. Observing the subtle distinctions between zones offers insight into the structure of lifelike processes without invoking organisms beyond scientific plausibility. If we imagine larger microscopic mats connected to vent areas, their surfaces could gently rise and fall with thermal flows. Plumes of warmer liquid push them upward slightly, while cooler surrounding layers allow gentle sinking. These vertical movements combine with horizontal currents to create three-dimensional patterns of slow motion. Observing from above or within mid-depth layers, one can see faint, continuous rearrangement that maps the energy and chemical gradients in the liquid. The process is entirely governed by physics and chemistry, with motion visible yet predictable. Light continues to play a subtle role. Particles near the surface or in shallow layers interact with it differently than deeper structures. Faint glows or reflections move as the liquid shifts, revealing slow patterns that follow currents and chemical differences. Deep areas are darker, but gentle contrasts in light intensity can indicate where plumes, particles, or small clusters are concentrated. Observing these contrasts carefully, one can trace the invisible pathways of energy and motion within the ocean, learning how chemical and physical forces structure activity. Even the faintest micropatterns respond to changes in pressure and density. As we move deeper, rising plumes slow slightly, sinking currents compress, and particles adjust accordingly. This layering ensures a stable but dynamic system where each microcomponent contributes to the overall motion. Observing over time shows continuous interactions between light, chemistry, density, and currents, forming organized but subtle patterns across the alien ocean. Each motion, each drift, adds to the ongoing story of this liquid environment. Clusters of particles may occasionally merge or split, forming temporary aggregations. These changes are slow, responding to local currents or chemical gradients. They illustrate natural processes without invoking complex life. Over time, clusters shift gradually across the liquid, tracing energy paths, reacting to temperature differences, and adapting to density variations. These slow, observable changes demonstrate the organized behavior that emerges naturally from simple components in the ocean's chemistry and physics. The effect of currents on these clusters is continuous and gentle. A slow, steady flow carries particles along the surface or mid-layers, while subtle rotational motion at the edges of wakes creates small, swirling patterns. Vertical gradients move particles up or down without abrupt changes. Each motion connects to the larger system, showing how microscopic activity mirrors the broader dynamics of the alien ocean. Observing patiently reveals the patterns, relationships, and flow pathways that are always present, even when life is reduced to microscopic scales. In zones influenced by chemical plumes or vents, particles follow subtle, predictable paths. Rising lighter streams lift structures gently, while surrounding layers resist, producing faint vertical displacement. Horizontal currents carry them outward, gradually dispersing them. Over time, these slow motions trace invisible highways within the ocean, mapping energy, chemical composition, and density in a seamless, continuous display. Each pathway is observable, measurable, and entirely consistent with known physics and chemistry. The potential for faint bioluminescence or reflective properties in microscopic mats is subtle but scientifically plausible. Localized chemical reactions, or differences in density and light exposure, could produce minimal glows. These would not be large or dramatic, but visible when the eye is attentive. Currents, waves, and layering gently shift these glowing regions, creating moving patterns that reveal interactions between particles in the liquid. Observing them is a study in continuity, connection, and the slow rhythm of the ocean environment. Overall, these microscopic and chemical structures show that the alien ocean, even without large organisms, is a system full of movement and subtle activity. Floating mats of particles, plumes, and gradients interact with currents and temperature layers. Each motion is slow, steady, and continuous. Patterns emerge naturally from physics and chemistry. Watching these dynamics carefully provides insight into the potential organization of ecosystems based on what is scientifically plausible, emphasizing the calm, slow, and connected nature of this alien marine environment. From above the surface, the motion of the alien ocean begins to reveal larger patterns. Subtle lines in the water hint at currents moving across great distances. These flows are shaped by the planet's rotation, forming broad arcs and gentle loops. Currents carry both liquid and floating features steadily, creating faint, continuous pathways that stretch for hundreds of kilometers. Observing these movements slowly, it becomes clear that the ocean is not just a collection of small ripples and eddies, but a large, integrated system where energy travels through the liquid in predictable, rhythmic ways. Planetary rotation influences the direction of these flows. The Coriolis effect causes currents to bend gently, creating spiraling motions that repeat over long distances. Gyres form naturally, slowly turning in circular patterns. These motions are continuous and stable, linking surface currents to deeper layers. Even small floating objects follow these pathways, tracing the invisible lines of motion created by the rotation of the planet. Watching patiently, one can see how planetary dynamics shape the behavior of the ocean on a scale far larger than individual waves or local currents. Tidal forces, if present, influence surface motion as well. Gradual rises and falls in liquid level create slow movement along the horizontal plane. These motions are barely perceptible in the short term, but contribute to the long term circulation of the ocean. Subtle differences in height and pressure move liquid gently, guiding currents into predictable paths. Observing tides over time reveals a continuous flow of energy through the water, connecting distant areas and linking surface motion to underlying dynamics. Wind, if present, adds another layer of motion. Breezes along the surface push small waves and floating particles, enhancing currents in certain directions. The combination of wind driven flow, tidal movement, and rotation creates layered patterns of motion that are both continuous and observable. Surface ripples align with these larger currents, tracing the direction and speed of movement. Watching these interactions slowly allows perception of how multiple forces combine to shape the large scale rhythm of the ocean. Deep currents move independently but are connected to surface motion. Denser, cooler liquid sinks in some regions, while lighter, warmer liquid rises in others. These flows form vertical loops, slowly transferring energy and material from one layer to another. The interaction of vertical and horizontal currents creates subtle variations at the surface, visible as faint streaks or differences in wave behavior. Observing carefully, one can see how energy moves through the ocean steadily, linking surface patterns to deep circulation. The structure of gyres and circulation zones becomes apparent when floating features and surface ripples are followed over long distances. Clusters of particles, mats, or mineral formations drift along these slow arcs, tracing the invisible highways of motion. Currents carry them continuously, forming patterns that are rhythmic, connected, and predictable. These flows interact gently with smaller waves and local eddies, producing a seamless combination of small scale and large scale motion that reinforces the overall stability of the ocean system. Energy from planetary rotation also manifests in subtle waves that propagate across the ocean. These are not sudden or sharp, but slow, rolling movements that can be observed over extended areas. Floating objects drift along them, rising and falling slightly as the liquid moves. The continuous propagation of these motions shows how energy from large scale forces is transmitted through the ocean, creating a rhythmic system of flow that is steady yet dynamic. Observing over time highlights the natural organization that emerges from the interplay of rotation, tides, and liquid properties. Light reveals these currents in indirect ways. Differences in surface texture, reflectivity, or color trace the motion of water. Slight changes in wave orientation indicate flow direction, while subtle swirls mark the edges of circulation zones. Observing carefully allows the eye to map the large-scale patterns without relying on direct measurement. The ocean appears calm at first, but slow, continuous inspection reveals the underlying motion connecting surface, subsurface, and deep layers. Currents interact with floating and submerged features continuously. Islands, ridges, and mineral formations slightly divert flow, creating small eddies and gentle wake patterns. These local disturbances merge with larger currents, contributing to the overall energy distribution. The motion is gradual, with no abrupt shifts. Floating clusters of particles drift along these flows, demonstrating the connection between visible structures and invisible forces. Over time, a map of motion emerges, showing how planetary rotation, wind, and density differences shape the ocean as a coherent system. Vertical and horizontal interactions combine to create complex but smooth patterns. Rising warmer liquid meets sinking cooler flows, forming gentle countercurrents that merge over distance. Horizontal gyres intersect, forming zones of slow convergence or divergence. Surface ripples and small waves respond to these patterns, reflecting the layered motion beneath. Observing continuously allows one to perceive how the ocean functions as a connected, rhythmic system, with each part influencing and responding to the others. Tidal forces, currents, and rotation interact predictably over long distances. Some regions show slow, steady movement in one direction, while others rotate or form loops. Floating particles would trace these paths faithfully, moving continuously along the invisible tracks laid out by planetary dynamics. Currents bend around large submerged structures, forming gentle arcs that link surface features with deep motion. The ocean is a connected system, its rhythm shaped by planetary scale forces acting through density, temperature, and chemistry. The flow of energy through the ocean is continuous. Dense liquid sinks, lighter flows rise, and horizontal currents carry material along gentle arcs. Subtle interactions create faint eddies, swirls, and surface streaks. Even small waves align with these patterns, reinforcing the steady movement. Observing these flows from a moving perspective allows one to see the rhythm of motion as a whole, a natural balance between forces acting across multiple scales. The ocean's movement is a coherent system, fully integrated from surface to depth. Wind and surface currents produce faint but noticeable streaks on the water. These lines follow large-scale gyres and minor flows, linking the surface with deeper layers. Differences in color, reflectivity, or wave orientation reveal the underlying structure. Careful observation over time shows that motion is continuous, guided by physical laws rather than chance. The ocean carries energy from one region to another, transmitting it smoothly through the liquid. Every ripple, wake, or swirl is part of the larger pattern, demonstrating the slow, connected dynamics of the alien ocean. Even subtle shifts in temperature and chemical composition influence these currents. Denser regions resist flow slightly, while lighter areas move more freely. Currents bend, merge, or separate gradually, forming continuous arcs that persist for long distances. Vertical interactions link surface and deep layers, while planetary rotation ensures circular patterns form in broad gyres. Observing these patterns slowly develops a perception of the ocean as a single, connected system, with every motion part of an integrated whole. The rhythmic motion of the ocean conveys a sense of order and continuity. Surface streaks, swirls, and eddies trace the paths of large-scale currents. Rising and sinking flows indicate vertical transport. Faint waves carry energy from one zone to another, guided by rotation, density, and temperature. Each motion interacts subtly with nearby flows, forming a slow, repeating pattern that connects the entire system. The ocean appears calm, yet dynamic, a continuous, observable network of energy, of flow, and interaction guided by the planet's physical forces. As we rise slightly above the ocean, the sky begins to draw attention. Light from the stars slowly moves across the horizon. Its angle changes gently over time, brushing the top of clouds and casting long, soft shadows across the liquid surface. The water reflects these changes in light, forming subtle bands of brightness that shift with the motion of waves. Even small ripples catch the star's glow differently, creating a patchwork of faint highlights that move continuously with the currents. The effect is calm, steady, and easy to observe, revealing how the liquid and sky respond to each other. The atmosphere filters and scatters light. Depending on its composition, the sky may take on colors ranging from pale blues to muted greens or soft yellows. Cloud layers block some rays and bend others. Shadows stretch across the ocean in slow, continuous movement, forming shapes that change as the star moves. Light bending at the edges of clouds creates faint gradients, soft transitions between brightness and shadow. Observing these subtle variations allows one to track both the star's movement and the patterns of the atmosphere in a gentle, immersive way. Reflections on the water follow the same rhythm. Calm areas reflect the sky almost like a mirror, showing clouds and the stars' glow. Moving currents distort these reflections slightly, bending light in slow, flowing arcs. Small waves scatter light, forming shifting lines and patches that trace the motion beneath the surface. Even floating particles catch brief highlights as they move along currents, adding soft sparkles to the overall display. The combination of sky, clouds, and ocean surface forms a continuously changing canvas of light and color. As the planet rotates, the star's position changes gradually. Shadows lengthen or shorten, and reflections move accordingly. The horizon shifts subtly, altering perspective and revealing the curvature of the ocean. Over extended periods, light angles produce slow transitions from brighter areas to deeper shades. Patterns on the surface change in harmony with these variations. Observing this motion quietly, one can perceive the passage of time without sudden or abrupt changes, allowing the mind to settle and follow the rhythm naturally. Stars beyond the primary light source begin to appear in darker regions of the sky. Their faint points are steady, contrasting with the moving light of the star. As the star rises or falls, these stars shift position slightly, indicating the planet's movement in its orbit. The reflections in deeper or calmer parts of the ocean create pinpricks of light, tracing the surface motion subtly. The combination of celestial light and surface reflection produces a gentle interplay of brightness, shadow, and motion that can be observed continuously without strain. Cloud shadows move slowly across the ocean surface. Thicker clouds create darker regions, while thinner layers allow streaks of light to pass through. These patterns shift gradually with the wind, tracing both atmospheric motion and liquid currents. Watching them over time shows how energy from above interacts with the ocean, producing gentle variations in temperature, light, and reflection. The movement is continuous, predictable, and calming, revealing the relationship between sky, clouds, and ocean in a simple, observable way. Refracted light along the edges of clouds and the ocean creates soft gradients. Rays bend when passing through varying densities of atmosphere or liquid. At shallow angles, these effects are more pronounced, forming faint arcs or glows that stretch across the surface. They move slowly as the star's position changes, creating a dynamic yet subtle display. Floating features or small waves may catch these rays differently, emphasizing their motion and texture. Observing the effect develops a sense of depth and connection between the atmosphere and ocean surface. The transition of light over time is gradual. As the star rises higher, the water brightens, showing more details in waves, currents, and floating features. Shadows shrink and become sharper near vertical rays. When the star lowers, light softens, angles stretch, and surface reflections take on warmer tones. The color gradient moves slowly across the sky, mirrored by subtle changes in the water. This continuous shift allows one to perceive day and night cycles or orbital effects without abrupt contrasts, maintaining a calm, steady rhythm. The star's movement interacts with cloud density and atmospheric composition. Denser layers filter light more, producing darker bands in the sky and muted reflections in the water. Thinner regions allow brighter shafts to pass through, highlighting waves or floating structures. The interplay of these effects is continuous, never sudden, forming a natural pattern that evolves steadily over time. Observing this interaction gently shows how light, atmosphere, and liquid form a connected system, each responding to changes in the others. Shadows cast by clouds or distant features on the horizon travel slowly across the ocean. They stretch over ridges beneath the surface, and floating formations. Even subtle elevation changes in the ocean floor can create faint differences in reflected light. Watching these movements patiently reveals a continuous story of how light interacts with the planet's topography, atmospheric layers, and ocean surface. Patterns evolve gradually, never abruptly, giving a sense of calm order to the environment. Reflections from floating particles or mats respond to the changing light. Small features appear brighter when light catches them at certain angles, then fade as shadows pass. Their movement along currents is mirrored in shifting highlights, creating a subtle animation that traces both motion and illumination. These visual cues provide insight into the continuous interaction of motion, reflection, and light scattering in a liquid environment, making the observation slow, steady, and immersive. Celestial patterns in the sky shift with the planet's rotation. Stars, faint and steady, move relative to the moving star, showing the slow progression of the planetary day. Their visibility depends on the light from above and the density of atmospheric layers. Reflections in calm water amplify these movements subtly, creating a continuous but observable rhythm. Over hours, the combination of direct light, scattered rays, and faint celestial points traces a natural passage of time across the scene. The ocean surface mirrors gradual changes in light and color. Currents carry floating structures through reflections, making patterns that repeat and evolve slowly. Waves bend and refract light, producing moving gradients and soft sparkles. Even distant ridges or submerged features influence how light bends, casting faint, continuous shadows. Watching these interactions over long periods reveals the steady rhythm of energy passing between sky and ocean. As the day progresses, cloud shadows lengthen and shorten, light intensifies or softens, and reflection shifts subtly. The combination of planetary rotation, atmospheric scattering, and surface texture produces a continuous dance of light and shadow. Observing in stillness, one can follow the movement naturally, noticing details in waves, reflections, floating mats, and cloud shapes. Every element is part of the system, and the motion is continuous, gentle, and calming. Even in low light or twilight, the surface retains traces of reflected celestial light. Stars and faint glows from particles combine with residual sunlight, forming soft, shifting illumination. Currents carry particles along smooth paths, changing the reflections gradually. The effect is subtle, never abrupt, forming a natural, immersive display. Watching over time gives the mind a sense of quiet continuity, highlighting the slow, predictable rhythm of the ocean, atmosphere, and celestial motion as an integrated whole. We begin to rise slowly above the ocean again, leaving the surface behind. The gentle motion of waves, the subtle streaks of currents, and the floating features all recede gradually from view. The faint reflections of clouds and light linger for a moment before merging into broader patterns. From this higher perspective, the ocean looks unified, its motions interconnected from top to bottom. The gentle rhythm of currents, tides, and chemical layering remains visible, forming soft lines and arcs that trace the energy flow across the planet. The planet itself seems alive with continuous motion, even as we move farther away. Colors and textures change slowly as we gain altitude. The subtle gradients in the water, shaped by depth, temperature, and chemical composition, blend into a smoother surface. Small ridges and submerged features form faint shadows that stretch across the liquid. Floating particles and mats continue to drift, their paths tracing invisible highways of motion. Light reflects differently from higher vantage points, forming soft bands that move with the planetary rotation. Observing these patterns allows the mind to take in the full scale of the ocean's complexity, connecting surface and depth in a quiet, calm way. The atmosphere above is layered and continuous. Thin clouds float high, casting gentle shadows on the water. Rays of light bend as they pass through these layers, producing soft illumination across the planet's surface. Colors shift slowly, depending on the position of the star and the density of the atmospheric layers. Pale glows highlight ridges and minor waves, while darker areas remain in gentle contrast. Watching these interactions over time gives a sense of stability, rhythm, and connectedness in the environment. The system is continuous, linked from the sky to the ocean floor. Currents and motion remain apparent even from this altitude. Gyres and loops form broad patterns across the ocean, while tidal effects ripple subtly. Vertical circulation beneath the surface moves steadily, carrying particles and chemical gradients in a slow, layered motion. Floating mats follow these currents, tracing arcs that stretch across vast distances. The movement is never abrupt, it is continuous, predictable, and calming. Observing this at a distance allows the mind to perceive the integration of forces acting at multiple scales, from microscopic particles to planetary currents. Light continues to evolve with the planet's rotation. Shadows stretch and shrink gradually, while reflections bend and shift across the water. Glimmers from particles and mats follow faint paths, tracing both motion and composition. Atmospheric scattering softens the brightness in some regions while highlighting others. The star's position changes slowly, revealing long, continuous transitions between light and shadow. From this perspective, the planet's movements feel rhythmic and continuous, steady display that draws attention without demanding it. Floating features, though small, trace larger currents and arcs across the ocean's surface. Their movement remains gentle, guided by density differences, chemical gradients, and planetary rotation. Even tiny eddies around ridges or submerged formations contribute to the overall flow. Observing these patterns over time creates a sense of continuity, showing how the ocean's layered system functions as a single entity. The ocean is not separate from its atmosphere, light, or planetary dynamics. All are interconnected in steady motion. The reflections of clouds and light become softer as we ascend further. Subtle gradients stretch across the water, showing the interaction of surface texture, currents, and light. Floating mats and microscopic particles continue to drift along currents, maintaining faint patterns. These patterns connect the surface with deeper layers, emphasizing continuity. Even from this distance, one can perceive the organization of motion, the energy passing through the liquid, and the rhythm of the planet's natural systems. Temperature and chemical layers remain apparent in subtle ways. Denser or cooler regions beneath the surface influence surface patterns and reflection. Rising currents from vent systems continue to move faint streams of lighter liquid, tracing vertical motion. The interaction between surface and depth is seamless, forming a continuous exchange of energy and material. Watching from a distance allows these connections to be seen in broad perspective, showing the ocean as an integrated system of motion, light, and chemistry. The star's movement produces long, gentle transitions. Shadows lengthen across ridges and floating mats, while bright rays illuminate other areas. Light shifts across the surface gradually, revealing patterns in currents and waves. Celestial light from distant stars remains faint but steady, creating soft points in the atmosphere and subtle reflections on the water. These patterns trace the passage of time slowly, naturally, and continuously, adding to the calm, immersive observation. As we continue to rise, smaller details merge into broader textures. Waves form smooth gradients, floating mats blend into larger patterns, and light reflections merge across the surface. Currents form arcs and loops, visible at a planetary scale. The continuous movement of liquid, chemical gradients, and light show a connected system from top to bottom. Even subtle features like ridges, vent plumes, or particle clusters contribute to the ongoing rhythm. Observing these connections helps the mind perceive the planet as a whole, structured yet fluid, active yet calm. The atmosphere above also integrates with the ocean's motion. Clouds drift slowly, their shadows shifting over the surface. Light bends gently through atmospheric layers, creating soft glows and diffused reflections. Temperature differences in the atmosphere can create some faint vertical movements so that influence surface waves. Observing these interactions emphasizes the continuity between liquid and air, showing that motion, light, and chemistry are linked throughout the environment. The system is seamless, with no abrupt changes, forming a calm and balanced rhythm. From this higher perspective, broad gyres and circulation loops are visible across the ocean. Surface currents trace arcs connected to deeper flows, forming patterns that repeat over long distances. Tidal effects ripple subtly through the liquid, guiding floating mats and particles. Even minor disturbances from submerged ridges or vent plumes are integrated into the larger flow. Observing continuously, one can perceive the steady transfer of energy through the system, from small-scale currents to planetary-scale motion. Light continues to shift with time, producing slow transitions across the sky and ocean. Reflections on the water follow these movements, tracing arcs, streaks, and gradients. The interplay of direct light, scattered rays, and faint celestial points creates a natural rhythm that repeats gently over hours. Surface currents, microscopic structures, and floating mats respond to these light changes gradually, maintaining alignment with broader motion. Watching this over time reinforces the sense of continuity and calm. Slowly, the planet recedes beneath us. Ocean patterns, currents, and floating mats shrink in perspective, yet their organization remains clear. The rhythmic movement of water, light, and atmosphere continues without interruption. Currents still form arcs, ridges cast subtle shadows, and faint reflections trace paths across the surface. Even at this distance, the integration of forces, rotation, density, chemistry, and light remains visible. The planet functions as a whole, and its motion continues independently, calmly, and predictably. As the narrator's voice fades gradually, attention is drawn less to specific details and more to the overall sense of motion and connection. The ocean, atmosphere, and celestial light form a continuous system. Waves, currents, chemical layers, clouds, and star reflections maintain their rhythm, flowing naturally without interruption. The mind can follow these patterns gently, noticing structure and continuity without focusing on minute details. Observation becomes more relaxed, the body settling with the steady rhythm of the planet. Colors, textures, and motions blend together into broader patterns. Shadows stretch across the ocean, light diffuses through the atmosphere, and floating mats drift slowly along currents. The planet continues to move, rotate, and circulate energy seamlessly. Currents trace arcs, chemical gradients shift subtly, and light bends gently across layers of water and air. The integrated system remains continuous, showing motion without abrupt change. Observing this, one can feel the calm and predictability of natural systems on a planetary scale. Finally, the focus shifts from individual features to the overall rhythm of the environment. Surface waves, microscopic particles, and chemical layers all contribute to a steady flow. Currents, tides, and rotation create repeating patterns. Light shifts slowly with the star and orbital motion. Clouds drift, casting moving shadows. Celestial points remain constant yet faint. The ocean functions as a connected, integrated system, its motions continuous, layered, and harmonious.